What's the biggest impact you can make with your career? Medicine or engineering? For Sarah Wandelt, this question has a personal twist. While Sarah originally set out to become a medical doctor, her career led her to the fascinating world of neuroengineering and neurotechnologies. Meanwhile, her twin sister, who had dreamed of being an engineer, is now a medical doctor. So, how did they end up switching roles, and what insights can Sarah share with aspiring professionals in neuroscience and neurotechnology? In this episode of Neurocareers Doing the Impossible, your podcast host, Dr. Milena Korostenskaja, or simply Dr. K, interviews Dr. Sarah Wandelt on her exciting journey from her groundbreaking work on speech-brain-machine interfaces, BMIs, to her cutting-edge research on decoding internal speech signals. As a neural engineer at the Feinstein Institutes, and a former postdoctoral scholar at Caltech, Sarah has been at the forefront of developing technologies that translate brain signals into speech, offering life-changing solutions for people who have lost their ability to communicate. Her publication, A Representation of Internal Speech by Single Neurons in the Human Supramarginal Gyrus in Nature Human Behavior, showcases how decoding internal speech is not just a possibility, but a reality. Sarah will share insights into how brain-machine interfaces can decode internal speech and how her work is opening new frontiers in neurotechnology. Curious how a career in neuroengineering can impact lives? Or how decoding the brain's inner voice is revolutionizing communication? Tune into this episode as Sarah Wandelt shares her journey, career advice, and her fascinating work in speech BMIs. Get ready for an inspiring conversation about innovation, neurotechnology, and building a career that makes a difference. Hello, Sarah. It's a great pleasure to have you today on our podcast. Thank you very much for coming. Can you please briefly introduce yourself to our listeners and tell them where you are joining us from what part of the world?
Yes, absolutely. Thank you so much for having me today. I'm very excited to be here. So my name is Sarah Wandelt, originally actually from Switzerland, or at least I've lived there from the age of 13. That's where I first studied and got into the world of bioengineering and neuroprosthetics. And then I did my PhD in the Richard Anderson Lab at Caltech. That was located in California, near Los Angeles for a while. That was very nice. And then I most recently relocated to New York City. I'm working now as a neural engineer in a research lab with Professor Chad Boughton.
That's so interesting. I've just recorded a podcast with him the day before yesterday.
Oh, we didn't talk about it. I didn't know that. Oh, that's really fun. I was wondering if you would talk to them because I know you've been talking to people from the
Yes.
that participate in the PCI competition.
Yes, and Dr. Boughton's project, and of course, all his team's project, it was nominated for the BCI Award in 2023. So this is what we talked about. So thank you for introducing yourself, Sarah. And my next question is about your past. Maybe we can take a step back and you can tell us, how did you come to this place where you started working with neural interfaces, with neuroprosthetics, becoming a neural engineer? Maybe you can recall yourself as a little girl. What were your aspirations? What did you want to become? And what was that path that led you to neural engineering?
Yeah. I think when I was younger, this sounds very cliche, but I always wanted to do something where, I would help people. So for the longest time, I thought I wanted to study medicine. And I did really think that until more or less the last year of high school. And then I somehow switched and decided that helping people as a doctor is obviously an amazing career. But at that moment, I was like, oh, maybe, I felt like very empathetic. And I was like, maybe it's going to be so hard to work with patient populations every day. but I really, really liked biology, and I really liked, learning about the human body. And so I decided that I wanted to study bioengineering because I thought that would allow me to still study, the human body, like the biology, would also allow me to work on technologies that would maybe help even more people than, as a physician. So I didn't have a concrete plan in what exactly I wanted to do when I started studying bioengineering. I was very lucky that I lived close to a very good school in Switzerland that is an engineering school. It's called École Polytechnique Fédérale de Lausanne. And so I started studying bioengineering there. They actually have a lot of professors in the field of neuroprosthetics. So this is where I first got introduced in the world of neuroprosthetics. And I immediately thought it was super fascinating. So I started my master's. So in Switzerland, or in Europe, most people do a bachelor's followed by a master's. And during that time, I was able to take some classes, specifically in neuroprosthetics. I immediately thought, wow, this is such a cool field. I want to learn more about it. And so they actually even offered a minor in it. So I had the possibility to start working in that field. They mostly work on non-invasive techniques. So I got some experience doing projects using EEG and EMG. And I immediately found that super fascinating. And so at that time, I was working on a project with Professor Milan. And I asked him if he had any contacts in the US to do my master's projects. We were doing really cool work with non-invasive technologies. In Europe, at least at that time, it wasn't very common to do any invasive type of work. So I was really interested to get more experience with more invasive techniques, as you can do really cool things with EEG and EMG, but the amount of data you get and like the amount of decoding you can do can be a little limited because there's so much noise and the quality of the data is not always the best. So he put me into contact with Professor Richard Anderson at Caltech. And so I joined there to do my master's thesis. And after 2 months there, I enjoyed the environment there so much. I thought it was such an incredibly cool lab. We're doing such incredibly interesting work. I like working with the participants. I like the people in the lab that I, on a whim, decided to apply to a PhD. The deadline to apply was actually, so within 1 month, I did my application for a PhD to join that lab because I just thought that was the coolest thing I'd ever done. Like this kind of work was just so, so interesting. And so, yeah, that's how I ended up working in the lab of Professor Richard Anderson and started my PhD there.
Thank you so much for sharing this. And one very important thing, I think that you mentioned that there are many ways how we can help people. So that genuine intent to help people and to go to medicine, it's of course very applaudable. However, there are other ways to help people. And actually, this was one of the main reasons why I wanted to start this podcast, because I had so many students, because I'm teaching neuroscience related classes, and majority of the students, they all wanted to be medical doctors. And I was wondering, what is the reason for almost all of them to just want to be medical doctors? Because they want to help people. And I wanted to show that there are more ways to help people than just to become a medical doctor. So what you said is so aligned with that. So how did your perception change over time when you decided, I will try to do something different, and you went on this path of neural engineer? How do you see it right now, the path of being a medical doctor versus what you did, just reflecting back on your decision?
So something that I didn't exactly mention. So I have a twin sister. The funny thing is that she wanted to be an engineer because she was good in math and physics, and I wanted to do medicine because I was more interested in biology and chemistry. And the last year of high school, we just both switched, and she became a medical doctor, and I became the engineer. So that was somewhat of a funny coincidence, and we both don't really exactly know how that happened. But I've had actually the chance to see how it's like to be a medical doctor compared to being an engineer, and it's really quite different pathways. I would say both are very interesting, and I have to completely honestly say that for now, she's probably helping a few more people than I am. We just happen in the field of bioengineering with brain machine interfaces, we just happen to be So I would say at the beginning of it that we're currently mostly working with like one or two. I mean, over the years, I've probably worked with 4 or 5 participants now. And obviously we're building towards the future where we're hoping that everything we're doing is going to be able to help thousands of people. If we think about the fact that how many people are affected by ALS or how many patients are affected by spinal cord injuries, those are thousands of people. But I will say that she is probably helping more people every day than I am doing right now, though. But who knows, maybe if you look back in 50 years, there will be some implications of my work that will also have helped a lot of people. I still think it's a very interesting decision to do. I do think both are incredibly important and valuable, and we need both in the world, that is for sure.
Yeah, thank you. Thank you for mentioning that. So let's now get to the topic of what you did during your thesis. I think that's very, very interesting work. I really would like us to go into more details. So maybe you can provide first just a brief summary of the work, and then we will go into more detail.
Yes, absolutely. So in my work, or at least in I think the paper that we want to discuss more in detail today, we studied if we can decode internal speech from participants using intercortical UTA arrays. So the participant that I worked with in the study, or actually I worked with 2 different participants in those studies, those are actually participants that they have spinal cord injuries, but they're still able to communicate. However, we discovered during the duration of my PhD, and maybe we can get into that when we talk about it more in detail, because actually our lab is originally working more on motor decoding, but really focused on the posterior parietal cortex. Well, nowadays we also have implants that are in other brain areas, but we're always very interested in the posterior parietal cortex and sensory cortex. And we were mostly working on trying to see if these brain areas could give us additional information for grasping processes. So to give participants with tetraplegia more independence. What they really like to do is, being able to grasp again. But the posterior parietal cortex is such a multimodal brain area that we discovered that there's so many different stimulants we can find in that brain area. And so throughout my PhD, I really did the transition from first looking at grasping processes where I was trying to decode different hand shapes to discovering that this brain area was also very responsive to speech. And somewhat first actually happened as a control. And until we then discovered that there was all this modulation for those different speech processes. And once we discovered that, we obviously also wanted to figure out how far we can push that. It seemed like language was very represented in that brain area. But then once we discovered that we were able to decode these different language processes, we also wanted to know, hey, can we actually push it? Like, which part of this speech are we actually looking at? And we discovered that if we asked the participants to just think the word in their head as if they were talking to themselves, we also found strong modulation in the neurons that we were recording from. And that was something that, to this extent, not been seen before, I would say.
Yeah, thank you. So let's talk a little bit about what is already known, what has been already done in the area of speech decoding, because there are different ways how different labs, different teams are trying to decode speech. We know that some of them are using motor cortex. Some of them are trying to decode actually just the meaning of the speech from all over the brain. This from fMRI, but also from some depth electrodes in different areas of the brain. So there are different ways to do it. Maybe you can just give us a brief overview of what's done in the field, and then we will pinpoint the difference of what you do, because I think what you did was really unique.
Absolutely. So there's been really a ton of super impressive progress that has been done in the speech decoding world, especially in the last few years. It's been really incredibly how fast this technology has been developing. But what many people tend to do is that they tend to implant electrodes or maybe ECOG arrays over the motor or the premotor cortex. And from there, they're able to get very good signals when participants are trying to attempt to speech. So these motor attempts and these motor plans that are being formed can be decoded really well from the motor cortex. This still requires the participant to still be able to attempt to speak. Another way their technology also has been working really well. And so here I'm talking about like Eddie Chang's lab or the Chenoy lab with Frank Willett, who's leading that research, and also Sergei Stravinsky, who's been doing a lot of work in this field. So they've been really trying to decode these generated motor aspects. However, if the participant is not really able to attempt to speak, it's not really clear if that technology is still going to work. And so here I'm thinking about participants that might have amyotrophic lateral sclerosis. So these participants, if they're quite advanced in their disease, they might get into a condition called locked-in syndrome. This might not even allow them anymore to even attempt to speak. Or we can also think about people that might have aphasia, and so they're still able to completely think about what they want to communicate, but they just are not really able to generate that speech. And for these participants, it's still unclear if these technologies that rely on this motor movement being generated would perform really well or not. They have shown that silent speech they can decode as well. So this is more like miming, I would say, where the participant is still moving their mouth, but they're not generating any sounds. So for that, the technologies work really well as well. But it's still unclear if this technology works well for someone that is really just thinking of saying it, but not able to do the motor movement at all anymore. And so in our research, we actually were able to, just by asking the participant to thinking about the word without any associated movement, we really tried to make that as similar as someone that wouldn't be able to, generate a motor plan anymore. So we asked the participant to just think about the word. It's very specifically instructed, so not just randomly thinking about words and us trying to decode that. We had like a very limited set of words that we asked them to think about at specific times, and we tried to see if that would be represented in the neural data as well. And so we found this brain area that's in the posterior parietal cortex called the supramarginal gyrus, which also had been for the first time implanted in a human participant that happens to be also seemed to be very involved in this internal speech process as well. We first discovered that it was active during vocalized speech, so when he was actually speaking, but then we also found that when he was reading words, this brain area was actually even more active. And we were like, wow, okay, that's really interesting. That seems like to be a language aspect to it. It's also responding when he would hear words being said. Interestingly, the activity for that is a little lower than for the reading of words. And then we actually discovered that it was also active during internal speech. And so here we did some control experiments actually, because we were kind of curious to know like what is even going on during internal speech. And that is something that is actually a huge question. Like what even is internal speech and what does it mean to different people? If you ask different people how they think, or if they generate internal speech, you'll get a variety of different answers. Some people will say that it sounds like a little voice in their head. Some people don't think that there's any audio aspect to it at all. Some people feel like it's more like they might see words written on a screen. Some people might be very silent in their head and not really use internal speech much. So there's all these different aspects in their speech, and it is actually really hard to know what someone is doing when they're just thinking. And this has caused a lot of very interesting conversations, I would say, because how often do you actually go and ask someone, hey, how do you think about things? I think it's really fascinating. And I think it's a field that's somewhat understudied just because it's so hard to study this field. How do you actually think? Because people don't think about it that much. And I actually read some work that suggested that people are not very good in even saying how they think about stuff. So I think this kind of research has been hard to do. And so I thought it was really fascinating. And so one of the controls we did, because when we first worked out participant, we actually didn't instruct him specifically how to think about things. We just said him, if you were talking to yourself. So to me, I assume that means he has a little voice in his head and saying something. But then I talked with my professor about it. And he was like, why would it be sounding like a word? Like why would there be sound involved? And I was like, oh, wow, okay. So in your case, your inner speech doesn't have any sound component at all. We tried to compare the activity that we were seeing doing those different modalities. So we recorded brain activity while the participant was hearing a word. We recorded the brain activity when he was saying the word, and we recorded the brain activity when he was internally saying the word, and we also recorded the activity when he was reading the word on the screen. So we have all these different modalities, and we actually tried to compare how similar is the information between those different modalities. And actually what we discovered is that the activity between having a written word seen on the screen, reading the word, the inner speech activity was very similar to each other. The activity of vocalized speech and internal speech was also quite similar to each other, which actually is an indication that the supramarginal gyrus represent speech, not necessarily in the motor plan, but some sort of other speech function, which was also very interesting to see. But it was especially when we saw that reading the word and saying the word internally were very similar to each other that we were quite curious about that. And some studies have found that reading can activate inner speech, actually. So we thought that maybe that was a good explanation to see that the activity during these was quite similar in the brain. Because some people, when they start reading a word, they might just actually internally say that word. And so that might cause an activity that's very similar to inner speech.
Very interesting. Now let's dive even into more details. And my first question is, I will just go step by step. About the participants, you briefly mentioned that they had spinal cord injury. Can you describe a little bit more the participants? Were they, first of all, just about the participants, and second of all, about the arrays that were implanted? Yes, which areas of the brain? Because I know that you not only implanted in this posterior parietal areas, but also in the somatosensory cortex, yes? And actually those activations were slightly different between the silent speech and the vocalized. So I would like to get into all those nitty-gritty details from the very start.
Yeah, so in this study, we actually had two different participants. The first participant, so both of them have different implants, but we only focused on the implants that were in posterior parietal cortex, so the supramarginal gyrus, in S1 in the somatosensory cortex. We really actually used S1 in this context as a control area. So the participants are implanted there because we stimulate them as well to evoke sensations, which is part of a different study. But what we were able to observe is that S1 was active during vocalized speech. So the activity was very similar for each of the different words. So in our study, we had 8 words. 6 of them were vocalized lexical words. So that means they have a meaning to them. 2 of them were pseudo words. So those are words that sound like they could be a word, but they're not really a word. And we wanted to see if the semantic meaning of a word was necessary in order to have representation in those brain areas. But so what we saw is that the activity in S1 was very stereotypical for each of the words. So we were not able to decode from these words using data in S1. However, during internal speech, we were not able to see any activity at all in S1. And for us, that served as a control that the participant was really not moving during internal speech. As I mentioned, they are able to speak. So we wanted to make sure that during internal speech, there wasn't any like slight little movement that might have caused our results, and just really to make sure that the participants were not moving at all and that they were really, just trying to internally say the word. So S1 really stepped up the control area there. And we saw the same results in both participants, see indeed activity during vocalized speech, but we don't see activity during internal speech. So to us, that's hopefully an indicator that this would work also for participants that are completely unable to move anymore.
Thank you very much. Can you bring us into your lab experiment? When you are presenting the words, just how do you do it? What are the words? What are the instructions? So I really would like to imagine how they are being prompted to produce that internal speech. Yes, and then the comparisons with vocalized versus internal and other components, because as I understood, you had several components to the internal speech. So auditory imagination and visual imagination, and you mentioned this today, but how is it all presented? So how it is all done so that participants can imagine it all auditory and visually.
We have a vocabulary of 8 different words. 6 of them are lexical words, so with a semantic meaning, and those are words that we actually took from a study from Martin et al. In 2016. This was one of their latest studies that actually had found decoding of inner speech. They were able to decode words. They did pairwise decoding of words, and they found significant decoding during internal speech. So we thought this could be a good comparison to use those 6 lexical words that they had used. But we wanted to add 2 pseudo words to that, just words that don't have any meaning, because we wanted to know if meaning is important or not to see this neural activity. Another thing we were interested in seeing is if the way we would present those words would matter. So we either showed them the word on the screen, so that was like a written modality, so they would read the word, or it would be an auditory sound. So then they would just, from a speaker, they would just hear the word. And during that time, there would be a dot on the screen on which they would be focusing on, or during the written word, there would be the word appearing on the screen. And then after a short delay, there would be an orange dot that would appear on the screen. And here they were instructed to internally say the word. And here we didn't actually instruct them specifically how to perform internal speech. We just told them, say it as if you were talking to yourself, if you were saying that word. Like if I ask you, what's the name of your favorite animal? You might have a little voice in your head that comes up. But we didn't particularly tell them how to do it because we wanted them to be natural to them. So whatever the strategy would be. And so after a second delay, then we asked them to vocalize the word. And so we were also recording the audio while they were doing that. So we were able to make sure, that they were speaking the vocalized speech and not doing the internal part at all.
Yes, thank you so much. And the next question is, because you mentioned that different people might have different strategies in producing internal speech, did you assess your participants after they did the task? How did they approach this imagination? Did they hear like their voice, something in the head, or did they imagine? So what was their strategy of that internal speech?
What we discovered, one of the findings that we had, is that the activity that we were observing during reading the word on the screen was very similar to saying the word. Most of the results that I'm talking about are actually with one of the participants. With the second participants, the results were much weaker. And so we didn't do all these control experiments because in general, while we were still able to decode at chance level, the results were not really high enough to do a lot of follow-up studies to really differentiate between how strongly the different modalities were encoded. The concept that there is activity there in two participants, but the activity was definitely stronger in one of them. So we focused on that participant a little bit more. Since we saw that the activity was so similar between the written word on the screen and the internal speech, we were wondering, oh, maybe the participant is doing visual imagination of the word. Maybe he's just having a mental image of the screen with the word appearing. And so we did ask him about it, but we also wanted to do a control experiment where we actually investigated that a little bit more in detail. He actually said it sounded like hearing a little voice in his head. So it has more like, if I asked him, is it more similar to the auditory cue, to the written cue? He told me it's more similar to the auditory cue. But we specifically designed an experiment where we prompted him, okay, try to visually imagine the word on the screen, or try to really just have a little voice and like try to imagine the auditory part of the word. So we asked him to specifically focus on specific aspect of the word. What we found is actually both were encoded quite strongly there. So there wasn't really a big difference. He actually did say that it was harder for him to do the visual imagination because that didn't seem natural to him. But both were represented there, and I would say that both of them do require inner speech. So it does seem that it wasn't just any visual imagination he was performing; it's really the fact to perform internal speech.
Yeah, so it wasn't the strategy specific that they used. So it really.
Yeah, it wasn't just one strategy that works. It seemed like several strategies were working and that they were all somewhat related to inner speech. So
yeah, that's such a fascinating topic in general. And you mentioned that we still don't know much. It's the field of cognitive psychology that studies, yes, how we represent the speech internally. And I think that's a beautiful addition, at least, to what we already know in the area, because you tried different strategies and even looked at the neural representation of how this is done. Very good. So let's now get to the part of the signal processing. That's probably one of the toughest part. Yes, how can we get the information from the signal that we record? Maybe you can give us some details on the signal processing side of things. How did you do it? Even, from the first part of pre-processing, filtering, what type of signals did you get? What type of data? And then I'm sure you used the language models. Yes, so just if you can give us some technical details of what you did.
Yeah, absolutely. So the method that we're using in the lab is we're using Utah arrays. So these are little implants. So the ones that we have had either 96 or 64 electrodes. So they get implanted in the cortex. So that requires a quite invasive surgery with a craniotomy. I will say that our participants, all supported that really well. And actually, one of the participants where I got the best results with had been implanted for 5 years. So there's quite, at the time of me doing the experiments, now he's been implanted for 7 years and he's still part of the study. So it's kind of impressive how well some of these signals can prevail, even with Utah arrays that are known to have sometimes this loss of neurons over time that we're recording for, which we also observed. But yeah, just wanted to mention it. He had been implanted for 5 years at that point, so that's actually very impressive. And so with the Utah arrays, we are really able to record the activity of single units. So we might record from a few single neurons that are recorded just surrounding the tip of the electrode. And since we were getting single unit activity, we really focused our analysis on the spiking data. So the high, like we extract them using high frequency filtering. So we use quite a similar pipeline as other labs have done as well. I know it's now getting popular to also use spike band power, which if I were to go back, I would probably try to add that as well and see if that would improve my results. I think that can be a little more stable than just using spikes. But yeah, since we got pretty good spiking data, we were using that. And so we were able to get, say, between 30 and 60 neurons on each session day when we were recording. So what we would do is that we would record some training activity on each day. We would go to the participant. That data actually didn't have to be that much. So we were mostly doing this as a proof of concept. So really interested to see if we can actually get good results on like a single daily basis. So we would record 8 repetitions of each word just to get started with. And then we would train a decoder. So the decoder was actually fairly simple. It was based on averaging the activity during internal speech. That was around 1.5 seconds of data. One thing that I didn't even mention, which can be a little bit of a problem with internal speech, is that we don't really have any behavioral output to align our data to. So a lot of decoders rely on the fact that we can adequately align the neural data to the output that we're trying to get. And this is actually something that we don't get with internal speech. And while doing vocalized speech, we can use the audio to really define where exactly we're at. Doing internal speech, we don't really have that. So we really thought, okay, let's just as a proof of concept, use this activity during 1.5 seconds. We didn't even change that for the lengths of different words. We just assume we don't really know how long the word is, but we know that within 1.5 seconds, he had enough time to internally say the word. We averaged the activity of the neurons that were recording during that time. And then we use the linear discriminant analysis, which is really a fairly simple decoding algorithm to see if we could identify the different words from each other. And we did exactly the same thing also for the vocalized speech, even though there we have the audio, because we wanted to really be able to compare those results to each other, get better results with the vocalized because we're able to align it to each other. So even if only with 8 repetitions per word, which is something we were really able to get in like 7 minutes or less. And even that could have been quicker if we only had recorded internal speech. That could have been even quicker because we had this design of having a cue and then internal, then vocalized. So the trials could have been a little bit shorter, actually. So I think we calculated it's only 24 seconds of data necessarily per word that is going into that decoder, if you think about it. So it's really not a ton of data at all. But even with 8 repetitions per trial, we were already able to get pretty good results. And so we would train a decoder, test the decoder in real time. So then we would ask the participant to repeat the experiment, but this time, we would replace the speech phase by a phase where he was getting some output. So we would show him the word that was decoded on the screen. That allowed us to get more data. And so each time we were getting more data, we would just retrain the decoder to just get a little more data into it. And we were able to get over 90% classification accuracy on certain trial days. And so, of course, we only have 8 words, so that's not necessarily enough to, communicate. But it's a really good proof of concept to see that it seemed like these signals were quite strongly encoded in that brain area.
Yeah, thank you. And with the current development of AI technologies, how did all this new development help you in your work? Did you use any new algorithms, any new approaches that became available recently? And so did you integrate any of that into your work?
So we didn't really even have that much data to the point where I think that doing much more complicated models wouldn't actually have done much better. I'm not part of the lab anymore, so I'm not really involved in that work that much anymore. But I think a very popular technique people have been doing is to decode phonemes. And that's much more, if we can decode phonemes, that's going to allow us to expand our vocabulary size to, a much bigger number than what we currently have. Another technology also that people have been using is to do a speller with different letters. So Metzger has done a study on that recently. Like people in the lab are going to continue to work on that, expanding that a little bit. There's many different ways to do that, but I have to say that personally, since we only had this limited vocabulary size, there wasn't actually any need to go much more complicated because, we wanted as a proof of concept to see if that even actually works. But yeah, there's been so much work being done recently that really shows that decoding phonemes or decoding letters and then using language models to improve those results and using deep learning really all can contribute to getting much, much higher numbers. All these additional steps can really help then to make the technology much more useful for participants.
Yes, absolutely. And you mentioned a study. You referenced it because you took those 8 words from that study to your study published in 2016 on internal speech as well. So, compared with that study, what are the new things that you showed, and how do you compare the result of your study with the previous one?
Yeah, so there were a few studies that existed. Most of them, so just to say, I know at least from 2022, if we compare results to non-invasive work like EEG, I think this is the state of the art in 2022. So they were mostly doing pairwise comparison of words. So each time basically trying to decode only one word from another. And I think they were getting around 60 to 80% classification accuracy, which is significant, but maybe not super informative if you think about, building a huge vocabulary. There were also some ECOG studies that had been a little more successful. Some of them had done pairwise classification as well and found significant decoding, but not necessarily with each participant, which is actually something that we had an issue with as well, that it didn't work the same in 1 or different people, which might remain the whole question of is inner speech the same in everyone? Who actually knows? I remember also a study from Pay et al. Where they're using ECOG, and I think they were doing 30 or 40% classification accuracy. One thing about all of these studies was that they were all done offline or not in real time. So they were doing like analysis after the fact and trying to get the best classification accuracy. So one thing we definitely improved in is that we did it in real time. So we were able within 1.5 seconds basically to tell the participant which word was being decoded. So that was definitely a step that hadn't been done like that. There was a study from Angberg with Christian Herf where they did a closed loop application where they could detect inner speech when a participant was saying it. So that I think was the only other inner speech study that was done in real time. And so they could detect when a participant was saying a word internally, but they couldn't decode what the word was. So they could just say, yes, there is like some signal here during the speech, but I think they weren't able to actually say what word it was. And I think their models were also trained on vocalized speech. So another novelty of our approach is that we entirely trained our model on internal speech. So that really means that we didn't require any vocalized speech at all, which is also something that our study hadn't done. So many studies that had decoded internal speech had actually trained their decoder on vocalized speech because the behavioral output is missing during internal speech. But we didn't do that. So we really only use internal speech data, which again causes challenges if you want to like improve that. And if you want to compare that to the amazing results people are getting with attempted speech, I think it would always be lacking behind that based on the lack of behavioral output. But we wanted to make a point that we really only use data during internal speech. So that is another novelty. Another novelty is also that we put our implants in the supramarginal gyrus, which is a brain area that hadn't been implanted before, not in that much detail with the Utah array. It shows up sometimes in studies where they use ECOG grids, and if they would describe which electrodes were significantly activated, And some of, I think, previous work from the Eddie Chang lab, some of the electrodes in SMG would also show up as being participating in speech decoding, but only looking at SMG, I think none have done that as well, at least for speech decoding. I think actually it does show up in some fMRI works for inner speech a little bit, which is quite interesting, but not really for decoding.
Thank you. If you would summarize the main results of your study, what would those be?
So the main result of our study is that we are able to decode internal speech in real time in participants that, were implanted with gluta arrays in the supramarginal gyrus. We also found that the activity between vocalized internal speech and written words is quite similarly encoded in SMG. And we were able to do that with 2 different participants significantly. We did see differences in the amount of decoding in the 2 participants. But all in all, this suggests that internal speech can be decoded from the supramarginal drivers.
Thank you. And what was the most challenging part of this project for you, and how did you solve this challenge?
I think a big part of this study was and it sounds a bit silly, but I was convinced myself that, these results were actually correct and, that we were not maybe, decoding something else that we were missing. We really wanted to make sure that we were really decoding internal speech. And when I say internal speech, since it's so hard to describe, I'm not really sure what exact part of speech we're decoding. There are many different parts of speech. So I say it's internal speech, but it could be some part of speech production that it's not obvious to know what exactly we're decoding. Could be also something higher level that we haven't really been able to test, but we really wanted to make sure that we're not accidentally decoding something else. So, and when we were able to do it in real time, I think we were really convinced that, yeah, okay, we're doing this in real time. And we even recorded the participant to make sure that, they weren't like moving their lips while they were doing it, just to really make sure, that the results were indeed due to internal speech. I think it was just such a big question if that was even going to be possible that we really wanted to convince ourselves that was true. So I probably would say that was not challenging per se, but something that I always kept in mind.
Thank you. And my next question is about something that was unexpected, some finding, something that you learned during this project that you didn't expect when you started the project. Yeah, so we always are thinking, we have certain expectations, but sometimes things surprise us. So what was that surprising thing that you discovered during the project?
Yeah, so if I'm completely honest, the entire internal speech project was a big surprise. As I mentioned, I started my PhD studying grasp encoding in the supramarginal gyrus, for which there was quite a lot of evidence that it should be encoded there. And so we found good results there. And the fact that so much language aspects were encoded there, which was just a huge surprise. And that really piloted my entire PhD. And suddenly I find myself reading all of these papers about speech, knowing that I was at the beginning reading everything about grasping. And I think one study that also really inspired me there is a study from Sergei Stravinsky where they actually decoded from the motor cortex different words. And so I was like, oh, okay, so there's evidence also in other motor areas that there's language encoded there. And so, yeah, it was this pivoting moment of like, okay, so I guess my PhD is going to be in a different topic now. And it was just really interesting to see what was represented there. We did actually follow-up studies, which, we also tried to investigate a little bit more phonetic aspects are represented in the neural data, and semantic aspects are represented in the neural data. These results are unpublished, so I might not talk too much about them, but we just saw really interesting results there where it seemed both semantic and phonetic aspects are represented in SMG, and I thought it was just really fascinating to see the variety of different stimulants that we can find in the posterior parietal cortex. That is something that I think is always going to be very impressive. That I think sometimes we tend to think, oh, certain brain areas are responsible for only a specific function. And then suddenly we have this small implant in one brain area that just seems to be responsive to so many things. And I'm not saying it's causally involved in there, right? Because I don't know if I deactivate SMG, does that mean that my inner speech is going to be affected? There's actually a few studies that have a little bit of evidence for that. I'm not saying that is necessarily the case, but just saying that it responds so strongly to it and correlates to it is just fascinating.
Yes, thank you. And what do you think became possible with after you completed this project that wasn't possible before?
Yeah, I mean, I would love to see this applied in patients that, are really locked in. They have done a few studies with locked in participants, and it seems really, really hard to, give them abilities to communicate again. And I would really love this being tested in participants that lost all their means of communications and seeing that successfully being done. That would be really great. Additionally, I think that it gave SMG a little bit more, interest, like an interesting new area that might be explored more for brain machine interfaces. We were able to decode grasp and speech from the brain area, which also has interest if we think about it. We can put one implant in one area and get a variety of different functions that might actually be a very convenient location for brain machine interfaces. So I hope the research in that field will continue.
Yes. And how do you see this field of speech neuroprosthesis, let's say 10, 15 years from now?
Yeah, that's a great question. I think the progress that we are seeing right now in academia is outstanding. There's really been an incredible amount of work done there. I think what user error research suffers from, and even ECOG, is that it requires these very invasive surgeries, and these technologies are not actually, novel. They've been used for a while, and it's not wireless, so it's not that easy to do that at home with participants. And so it's actually really cool to see that there are some companies that are working on really bringing this to people. So I think that the fact that companies like Neuralink and Synchron and Paradromics and other companies are trying to really commercialize this, I think should really allow this field to not just been done with, a few participants in academia and very few labs in the world, to actually bringing that as actually a solution for people. Maybe not in 10, 15 years, but I'd like to see that in the future, this actually can become an option for people that really need it. To be, yes, you can go to the hospital and you can get this implant and it'll help you to communicate. And it's not like just a few select people. There will be a lot of work that needs to be done for that. And I don't think it's realistic to think that everyone will have a, very invasive implant, but I'd like to think that there will be a lot of progress being done in that in the next years.
Thank you. And of course, right now, with the development of neurotechnologies, people, especially who don't know all the details of the project that's happening, are concerned with neurotechnology reading their minds. And of course, certain studies, they emphasize that they can decode only attempted speech. So to ensure that the person really needs to attempt the speech to decode it. But in your case, you were working with internal speech, which already is not attempted. Yes, so it's closer somewhat to how we usually think. In terms of that, how would you address those concerns that people may have about neurotechnology, really reading the thoughts and things like that?
I think firstly, we definitely need the collaboration of the participant in order to do any of this work. So we try to do this experiment and the participant doesn't participate and just doesn't, think about the words that we think that they're thinking about, or like is trying to do these tasks, it's not gonna work. Even anecdotally have, I was one time where we were testing the decoder and suddenly I just see the same word popping up over and over again. And I was like, oh, what's going on? And I kind of checked and he just had gotten a little bit sleepy and kind of nodded off. And I was like, oh, okay. So if the participant is not participating actively, we're not going to be able to do anything and we're not going to be able to decode anything. And I think that since we still ask the participant to specifically focus on individual words, that is still not comparable to actually be thinking about thoughts. There are studies that say that thinking is actually a very truncated version of speech. It's not the entire word being set out. And it's much more quickly and fluent and probably involves a lot of different mechanisms. Here, it was really like specifically to in one moment to like instruct him to think about just that specific word, which really I don't think would generalize at all if he was just randomly thinking about that word in a variety of different contexts. It's obviously, I will admit, a bigger concern. And I think that would need to be taken into consideration, that really make sure that we're not, able to passively read thoughts that people may have. I still think that technology is like attempted speech, where it's probably a good solution for many people, and that this technology for internal speech would be a little bit more for very specific cases where the others don't work. I think that internal speech will always be harder to decode than vocalized speech, and that, it really should be used in cases where either they're not able to attempt to speak, or the motor plans cannot be formed in certain specific cases, or maybe even the and premotor areas are affected. And so maybe we want to look into alternative speech areas to see if we can recover signals from there. So I think that, yeah, the ethics of that are obviously very important. For now, we have a proof of concept with 8 different words. And I think that is encouraging for people that might require it. But I don't think it's concerning at all for people that think we're going to put an implant in their brain during their sleep, and then in the morning we can read their thoughts. That is not something that is going to be realistic, because we cannot train a decoder without a participant trying to. There's no way we can know what's going on in your brain if you're not going to tell me, and if you're not going to do what I tell you to do.
Thank you. Thank you very much, Sarah. That's encouraging. Is there anything about this study that you want to mention before we switch? Because I still want to talk a little bit about your career development.
Yeah, so I think what I always really find admirable about these studies is how participants are involved in it. So the main goal of the lab is working on recovering hand sensation and grasping. And so we chose the location for our implants based on that. So I didn't really talk about this much, but we did our MRI experiments to find the locations where we wanted to put the implants based on grasping tasks. So we weren't trying to look for speech areas. So our participants are obviously, there because we're trying to help them to recover their ability to grasp and to feel sensation in their hand. But it's always very impressive to see their willingness to participate in experiments that might not have a direct advantage from themselves, but might help out someone else that is in a different situation. And so it was really great to see that our participants were happy to do these experiments, even if they might not have a direct benefit from it. And so I'm very grateful, and I always admire our participants for their willingness to advance the science, even if they might not actually be the one that will benefit the most from it right now.
Yes, absolutely. And what was the feedback from the participants after they participated in this internal speech decoding experiments?
So I think our participant thought it was a very cool experiment, and that he thought that, if we told them, hey, you're the first person ever that we can decode internal speech from, I think he thought that was pretty cool. He's not the type of person that really wants to be in the media or be involved much outside of the research. He's very happy to be part of the research, but not really looking for big fame or anything. So I think he likes the fact that it might help other people, and I think he also finds it cool, but he wasn't necessarily thinking, oh my God, I'm going to go in the news and tell everyone that we can't decode internal speech. Yeah, so I think as feedback was, oh, this is very cool. I guess for him, since it doesn't really allow him to communicate, I mean, he's able to communicate to his friend, he can speak to us. I guess it's not the same kind of impact than for participants that actually have lost the ability to speak and suddenly can use that to communicate again. So I think his feedback was mostly that he thought it was really cool, and that he liked doing it. I think he always likes doing real-time experiments because he gets feedback, and that's exciting to see. Yeah.
Yeah, thank you. And I would like us to talk a little bit about your career after you finished your PhD. So now you are at a different place. How did you choose this path? Because some people decide to go to industry. As I understood, you chose to still continue in academia. How did you make that choice, and what are you focusing on now?
Yeah, after my PhD. So I really enjoyed that field. And I have to admit that when I started my PhD, I thought even if I just do this kind of research in my PhD, and there weren't many companies around then at that time when I started my PhD. And I thought, well, even if I just do this during my PhD, I think it's such cool work, such interesting work. I would really love to stay in that field, but if that's only what I do during my PhD, that's fine. In the meantime, I feel like there's really been so much development in the BCI world that I could actually see myself doing a career in that. And so I a little bit had this two-body problem where my partner actually was looking for a job and found a job in New York City. And so I started to look around what kind of opportunities there are in New York City. And I was able to actually be introduced to Chad Boughton. Actually, I followed him on Twitter, which actually might be a good way for students to, find interest in people. If you're interested in someone, go and find what they're up to on Twitter, on social media. That actually might be helpful to get to know them. And I saw that they were starting to, have a lab, and I was able to hear about the fact that they were starting to recruit for people. And there he was opening a position as a neuroengineer. And that for me, I felt like was really a perfect fit because I love academia, but I wasn't necessarily sure if I wanted to do a postdoc. And so I feel like in this lab as a neuroengineer, I'm involved in a lot of the work. I'm not necessarily leading on my own project, but I'm involved in a lot of different projects and helping everything to set up. And I think that's something that I really enjoy. So here I'm working more on grasping again, actually. So returning a little bit to what I started my PhD in. The participant there, we've gotten some really cool results already where his arm strength has really improved. We're working on some prosthetic and or orthotic devices so he can try and grasp cups with his own arm and do things on his own. I think that's really, really cool. It's a little bit a shift from the speech world again. I definitely love the speech world still, and who knows, maybe one day I'll work in it again. But for now, I'm really happy to contribute to this project.
Yes, that's amazing. And we will be looking forward to your new advances, to your new projects. And maybe we can meet in a couple of years and you will tell us all about that. What do you think are those transferable skills that you brought with you from your PhD to this new neural engineer position that are helping you to progress with your work?
I think a lot of the skills that I learned in my PhD are incredibly valuable in this position as well. There's been also implemented computer errors. So I already had experience with analyzing this data. I think every lab a little bit of a different pipeline. So we're also looking more at LFP data in this lab. So and delving more into that and getting into more signal processing techniques. So I'm learning more about that, which is exciting. We also work with electrical engineers in the lab, which are building a lot of the hardware that we're using, and it's really cool to learn more about how to interface with that. So a lot of the skills, I think, just about how to do signal processing, how to build decoders, how to apply decoders in real time. I would say debugging a lot is a big skill that you learn that can be applied then. And I feel like in this field, I always wish I was a better computer scientist, a better electrical engineer, a better signal processing, a better, mechanical engineering. I just wish I always was better in everything because it's such a multidisciplinary field. But I will say that the PhD prepared me really well for this position because we work with similar kinds of data.
That's interesting. And you mentioned LFPs. At the beginning, you said that you wish that you would also analyze more LFP data in your speech project. Am I correct?
Yeah. So I did look into that a little bit during my PhD, but then, there was so much work to do. So I focused more on the dying rates because I was, getting good results with that. But I think I would now go back and probably add that pipeline as well and see if my results would improve a bit or get more stable.
Yes. So, and with all this new experience that you have, are there any other things that you maybe would do already differently in your previous studies? And specifically, maybe the speech study that we talked about.
Yeah, I think it's really part of a researcher to go look back to your old studies and think, oh man, I could have done those a little better. Just control for your experience. I would have probably tried to implement LFPs or deep neural networks. Actually, I would think that again, we got really good results with a simple decoder, which was a great proof of concept. Because if it works with a simple decoder, that means that there's potential for even better results. So probably, maybe increasing the vocabulary size a little bit, but a lot of the repetitions that we do in the end are to make sure our results are robust. We didn't have quite as much time with the participant that maybe some of the other studies have. So I got maybe 10 data sets with that participant, and it took quite a while to get those data sets. So I would say that my time was maybe a little bit more limited. And so I was not maybe necessarily able to get quite the amount of data as have been maybe used in other studies. But I would probably, go and improve the vocabulary and look at phonemes. And there's so many things one can always do with the data sets one have already recorded, but then, this is on the new grad students in the lab to figure out.
Yes, absolutely. For those new grad students that are coming, and for other people who are following similar footsteps, what would be your advice? What would be your suggestion for them to complete their project successfully, to advance their career through their work successfully as well?
I think that something that I struggled with is imposter syndrome quite a bit in my career. And so I think that they're telling people that they're there for a reason. Sometimes people believe that, oh, I accidentally got into this field, but I don't deserve to be here. That's something that I was thinking regularly. And I think in the end, that's not a very useful way to think about it. And it's also not true. You're there for a reason. And, take the most out of it, talk to people. Like I remember being scared of talking to people at conferences. I was like, oh, they will see I'm an imposter. But actually you realize that the longer in the field, you get to meet your colleagues, and you have the best conversation really at post-year sessions. And I think daring to talk to them and like building these networks and like, reaching out to people is really something that I had to actively like learn and get better in, and then see that, people in the field are nice, like they will not bite. Yeah, other than that, I think that obviously stay involved. I think Twitter can actually be a pretty good tool as well to keep up to date with the literature. Following the people that are doing the work you're interested in, it's probably going to be one of the first places you'll learn about it, because they will tweet about it. And you can learn so much also just from what people are talking about. Conferences, again, I think a great way. Unfortunately, during my PhD, we had COVID. So several years conferences were not really an option, or they were online, which was not quite as nice. But again, like really this networking is really just helpful to get to know the field better, and just hearing about opportunities and about what's going on. Yeah, then I think in my particular case, it was, being interested in a field, and then wanting to stay in it was something that I got lucky to do, because I think I was there at the right time when reaching out to Richard, and he had a position open for a master's student, but also then just a desire to stay in it, and, trying my best to really like get involved in that field. So yeah, I think if you have a strong interest in something and you really like it, I think that's really helpful. Don't just do a PhD to do a PhD. Don't just go into the field because you think that it sounds somewhat interested, but you're not really passionate about it. I think really liking the field is very important in this context.
Absolutely, I agree with you. Is there anything that you thought of as impossible during your life, during your career development, that at the end proved to be possible? And if so, how did you make that impossible possible?
So you're talking to someone with imposter syndrome. So there are lots of things that I thought were not possible. So my work ended up having quite a lot of interest, which was amazing, but also stressful, because then I had to go and present it, which was something that really stressed me out. And so I would like to, I did not expect at all that the work I would be doing would get so much interest, and, that there would be interviews and podcasts, and our work ended up being selected for a press conference at SFN, which was amazing. But so to me, it seemed so unexpected. So I think there's so many things that I didn't expect to happen. I think what really ended up being so successful is to really keep asking questions based on the data you're seeing. So my field was on grasping. I could have completely just focused on grasping and continue doing that. And there's tons of work that I could have done based on that. But it's the fact that I wanted to make control experiments for that grasping. And so basically, the first thing that I ever was interested in, really, which I thought was really curious, is that we had such a strong activity during the Q phase when we instructed participants to grasp something, in SMG specifically. And so I wanted to see, what exactly that was due to. And so all my control experiments where I could with an auditory cue, I could with a written cue, came from the fact because I really wanted to understand what was going on with cue phase. I was like, the activity there is so strong. I don't think it's just planning, or maybe it's just planning, but what exactly is it? I want to know what it is. And so I think this curiosity was really something that drove then my whole PhD and then ended up to pivot completely. So I think always staying curious about the work you're doing, looking at your data and just, trying to understand it is something that really led me to, pivot and doing something completely different that I really did not expect at all. I think there's two approaches to science. Some people, and I think there's the right way under parenthesis, where you think about an experiment and you design it really well, and then you get the data and you analyze it based on that. And then I think, and that's something maybe that's a little bit more into this field. I still remember a professor telling me that I went to him and I went to Richard with my results and I was like, oh, like I have these interesting results that I didn't expect it. And he told me, oh yeah, this is something can happen quite often in this field because we put implants in brain areas that have never been implanted before. So, we don't necessarily know what we're going to get and what to expect. And I was like, oh, okay, that's great to hear. I figured I was doing it all the wrong way around, but, um, sometimes you have to be curious and just see what is going to happen. So I think both ways can work out.
Yes, absolutely. There's so much for us still to discover, and we need to be open to that and ask questions. So, thank you for reminding all of us about this. And you also mentioned that you've given many talks. Unexpectedly, there was an interest in what you did. I'm curious, what was the most interesting question that you received during all these talks and presentations?
I think one of the questions I've gotten, and to be fair, I didn't even have a good answer to that, is that because people mentioned that, we can cross decode this like speech. We can cross decode really well. So, if I turn a decoder of one modality, then I can, I can test it on other modalities. That decoding works fairly well. And so, and asked before, so if I was to apply this in the real world, would my decoder then just activate if I do one of the other things that I wasn't planning to do? And I think that's something that needs to be really controlled for. I hadn't like tested it per se, how I would avoid a decoder that, is active doing vocalized speech and internal speech, or maybe doing reading and internal speech. Maybe if he starts reading it, the decoder would just start decoding. And I was like, yeah, that's actually a good point. That's something we need to be controlled for and to see if there's actually enough identifying differences between reading a word and saying it internally to make sure the decoder doesn't get activated.
Yeah, thank you. Thank you very much. Can you tell our listeners how they can learn more about your work, where they can find information, and maybe if they want to get in touch and maybe have questions about what you do, what would be the best way to do it?
Yeah, absolutely. So there are two papers that I published during my PhD, my thesis that can be found on Google Scholar. I'm also active on Twitter, so I would usually tweet about my papers. I think that's something that is something that at the beginning I didn't want to do. I don't love putting myself out there, but you can get a lot of interesting conversations. I will say you also might get on the wrong side of Twitter, and I once tweeted about the internal speech paper and it was retweeted a lot of times. And then I get people telling me that the Chinese will use this technology to exploit people and spy on people. And I was like, whoa, okay. We are going into spheres here that I didn't expect at all. So it's obviously, you got to be careful with that tool a little bit. But in general, I would say it can be interesting, even though since Elon Musk was taking over to, okay, don't mention that. So I'm on Twitter, so I'll tweet about my work. There's also a few articles that have been written about the work, so these can be quite informative as well. I actually quite like some of them because they'll be more accessible for a bigger audience. One of the papers, actually the one about internal speech, we also wrote a short research brief about it, so it's also a good summary about the work that we did, and it's also a little easier accessible than reading an entire paper, especially if you're newer to the field. And yeah, you can always reach out via email. Always happy to chat to people and answer questions. My data sets are also online. So if someone wants to have a look at the data set and play around with it, they're more than welcome to do so. I'm also happy to answer questions about it.
Okay, that's amazing that you mentioned the data set. So they're freely available and people can try analyzing them. Can you tell a little bit more about that?
Yeah, absolutely. So as part of the papers, the code is online and also the data is online. And so people can go and download that and, reproduce the figures and get access to the data. So it's not the raw data, it's definitely processed data, but there's already a lot of things that can be done with that. And for someone that might want to get into the field and just wants to play around with the data set, that would be a great way to do that. Actually, a lot of different studies nowadays put their code and their data online. So for someone that's interested in the field, they can really find a lot of different data sets to start working with.
Yes, that's great. And many people who want to get into the field, they're asking where to start. That is one of the possibilities for them to analyze the data. And they always can reference the figures that are in the paper to how they do, how they process the data. So it's a great learning tool as well. So thank you for mentioning that. And would you like to talk about anything that maybe I haven't asked you today? Maybe there is some question that you would love to answer, but I didn't ask.
We didn't talk too much about why did we see differences in decoding between different participants? And there's obviously many reasons for that. Having the exact same implant location is not that easy to do with different participants. And actually, particularly in our case, the brain area where they implanted it between the different participants looks quite different. Our implant was also smaller in the second participant. So we only had 64 implants. And something I think that's been quite known in the field is that if we get more data and better quality data, that we usually can decode much better. Another fun aspect of it is we are mostly able to decode two of the words that both happen to start with an S. So it could be also that we targeted a subset of the internal speech part, but not all of it. So there's a lot of different reasons for that. But we were still able to reproduce our results in a second participant, which is sometimes not that easy to do in this field.
Thank you. Thank you very much, Sarah. And at the end, as we are already ending our podcast, is there anything you would like to share? Just the last words of today's podcast.
I think that the BCI world is an exciting word that has so much potential and there's so much improvements that are being done there. And I am really excited to be part of this world. I'm so impressed by everything that's going on in this field. And I'm really hoping that we can push all of this work forward so that we can really continue improving the lives of many people that are affected by diseases or accidents or conditions that would really benefit from the help of this field.
Thank you very much, Sarah. Thank you for being such a wonderful guest on our podcast. All our listeners and I are wishing you all possible success. And I'm looking forward to seeing your new work and hopefully having you on our podcast in a couple of years to see the amazing updates. So thank you. Dear Neurocareers podcast listeners, thank you for joining me and my incredible guests on this exciting journey into careers in neuroscience and neurotechnologies. I hope you've been inspired by the stories of those turning groundbreaking ideas into impactful realities. If you are looking for more guidance on advancing your neurocareer, book a free consultation with me, Dr. K, your podcast host and neurocareers coach at the Institute of Neuroapproaches, the only career service dedicated specifically to the needs of professionals in neurotech. Let's take the next step toward your neurocareer success together. In addition to free consultations, the Institute of Neuroapproaches offers a variety of services designed to help you thrive in neurotech. First, professional development planning. We help you create a tailored career development plan, identify knowledge gaps, and equip you with the tools needed to achieve your goals in neuroscience and neurotechnologies. Second, resume and cover letter review. Get expert feedback on how to craft documents that are specifically designed for job opportunities in the neurotech field. Third, interview preparation. Sharpen your interview skills through mock interviews and targeted feedback, including soft skills, hard skills in neurotech, BCIs, e.g., MEG, live coding, and presentation preparation. 4. Networking and job search strategy. Learn how to effectively network and uncover job opportunities while standing out in the competitive neurotech job market. 5. Negotiation and salary advice. Receive expert guidance on negotiating salaries and benefits and determining a fair salary range for your desired position. All this and more can be found at www.neuroapproaches.org. Again, www.neuroapproaches.org. So, what are you waiting for? Let's navigate the path to success in the world of neurocareers together and turn the impossible into possible. We're looking forward to working with you.